Okay. We welcome Professor Hesheng Chen to tell us about the China Spallation neutron source, which is being built nearby in Dongguan. You know that in UST, nobody's doing that. Part of the reason probably is that people don't think about using neutron source because it's not readily available for this community. But that clearly is going to change. The question is, should UST take advantage of that? Professor Chen graduated from MIT, PhD in 1984, worked on the same thing. And he has been involved in almost every major project in high energy physics in China, working at CERN, working at DAISY, and he led the Beijing Electron-Positron LiDAR, and its upgrade now called BEP2. And I met Professor Chen in '93 at Cornell when he gave the plenary talk, National Photon Lepton Conference. And it was, I remember people very impressed that they thought having a Chinese physicist come give a talk, they may not understand his English, but Professor Chen is a beautiful talk. And so today, welcome him to introduce the neutron source. And at any later time, you want to know more about the neutron source or see how we can take advantage of that, you know that where to contact. Let us welcome Professor Chen.
Okay. Thank you very much for inviting me to visit Hong Kong University of Science and Technology, and especially thank Henry to invite to visit the Institute of Advanced Study. So the last time I gave a seminar here was 1991, long time ago. So I'm very happy today to introduce the China Spallation neutron source. This is the outline of my talk. So I will give a brief introduction to Institute of Energy Physics. And I will spend a little bit more time to introduce the neutron scattering and the applications. Then I will give the China Spallation neutron source project overview, construction progress, and promote neutron scattering in Hong Kong, and closing remarks. Maybe not all of you knew the Institute of Energy Physics. So the Institute of Energy Physics belongs to Chinese Academy of Sciences. The mother institute was established at 1950, called the Institute of Modern Physics. So they changed the name, reformed several times, and in the 1973, the Institute of Energy Physics became an independent institute for the particle physics. So now our institute is the comprehensive and the largest fundamental research center in China, both in number of employees and in the budget. And also is the largest institute in Chinese Academy of Sciences for budget and scientists and engineers. Some other institutes may bigger, but they basically is more technicians. Now we have about 1,500 employees. In addition, we have 500 PhD students. In the Chinese system, we can give the master's degree and PhD degree. And we also have 60 postdoctors. The goal of the institute is the International Center for Particle Physics, both for particle physics based on accelerate, also for the non-accelerated physics study. We also provide large scientific facilities for multiple discipline research. So this is give the major research field in our institute at the moment. So we have the charm physics at the BEPC2. We're working at the LHC experiment at Geneva for both CMS and the Atlas experiment. And we have Yang Cosmic Ray Observatory in the Tibet. And we're also working for the particle astrophysics, including the space program, every Chinese moon project has our detectors. And this is a hard X-ray modulated telescope, which will be launched by Chinese satellite in 2 years. The scientific goal is to looking for the black hole and the higher energy astronomy. And we have largest team for accelerated technology and applications. We have high luminosity E+, E- collider called BEPC2. And we have high power proton accelerate for the Spallation neutron source, which I will report to you today, and also for accelerated driving subcritical system. So you know the nuclear reactors is the critical system. Nuclear weapons are supercritical system. So-called subcritical system is we use accelerator to provide additional neutron source in the reactor. So then we have two advantages. One is we could burn the nuclear waste, convert the long lifetime nuclear waste into the shorter lifetime. That's very important for the nuclear power. Another advantage is with the additional neutron source, we could also use the uranium-238 or thorium, which is much rich in the Earth for the nuclear power. So this is the pilot, is the initiative project in the Chinese Academy of Sciences, work for the accelerated driving subcritical system. We also have a lot of studies on radiation technology, including the synchrotron radiation source and applications, spallation neutron source and applications. And based on those large facility, we have multiple discipline research, including the life science, nanoscience, energy, environment, and so on. So the Beijing Electron-Positron collider was built at the middle of last 80s. And we upgrade between 2004 to 2008. And the luminosity means the event rate has been increased by a factor 100 because we convert into the two-ring collider. So we obtained many interesting results. One of very interesting discovery is the ZC3900. This is 4 quark states. It's the charged charmonium. So these results was on the first of the APS, US APS highlight physics results at 2013 over the world. So it's a very interesting results. So it's the first time we saw the 4 quark states. Now there is a proposal to build a large electron-positron collider called circular E+, E- collider. And in the future, it could convert into the PP collider. So at the first stage is to study to make a precise measurement of the Higgs bosons and to looking for the new physics. And in the future, we could convert into the PP bar collider with the energy 50 to 70 TeV. So that's the ambitious project, but very interesting. And another important experiment in our institute is not too far from here, Daya Bay. I think just close the sea. Daya Bay reactor neutrino experiment. We made a process measurement of the sin theta 1,3. This is a neutrino mixing angle. So we obtained these results at 3 years ago, published results 3 years ago. Is the first determination of the neutrino mixing angle, sin theta 1,3. This is the one of fundamental constants, physical constants. So it's very interesting results. And it also opened the door for the future neutrino physical experiment. So, and for the future plan, we are working, the Chinese Academy of Sciences approved Juno. The detector also is not too far from here. Here is Hong Kong. So we use the Taishan and the Yangjiang. Each one has the 6 nuclear power reactors. So this is probably the world's largest power station, and we choose the middle point and make the underground lab to shield in the cosmic ray background. So this experiment is supposed to take in data at 2020. So beginning of the last January, we had a ceremony of the groundbreaking in the Jiangmen. So the site is in the Jiangmen, and they use the reactors in the Taishan and the Yangjiang. So I'm not going into details of the scientific activities in the instant energy physics. Today, mainly I would like to report you the spallation neutron source. Before I go into facility, I would like to give an introduction about the neutron scattering and applications. So the neutron scattering actually is complementary with the synchronous radiation to study the material structures. The synchronous radiation from the light source, they interact with the electrons of the atoms. So basically, they are more sensitive to the heavy atoms, heavy nuclei. So the light source is easy to construct and less challenging. The neutron scattering, they study the structures with the spallation neutron source. So we use the higher energy proton beam, very short proton beam. We hit the target, produce the neutrons. The very intense and very short neutron pulse. This neutron pulse could provide another probe to study the structure and the dynamics behavior of the matter. Compared with the synchronous radiation, the neutron scattering has the following advantages. Neutron has magnetic moment, so they can detect the material magnetism. They can detect the position of the nuclei, particularly sensitive to the light elements and isotopics. Because the isotopic has quite different cross sections with the neutrons. And the neutron has much more power for penetrate the large sample. So they can do in large engineering components for many studies. more important is the neutron could have studied the dynamics behavior in the matter, because the neutron has appreciate energy momentum relationship for many studies. So I just give some examples. Only neutron can study the magnetic structures, because neutron has a spin with the magnetic moment. So with the neutron scattering, we can study the collective magnetic excitations in a strong correlated electron system, high TC superconductor, colossal magnet resistive material, quantum and molecular magnetism, ferroelectric, and many other studies in the magnetism. Also, since the neutron has a spin, they can study the spin fluctuation in the complex fluid, soft mat, long, low dimension system, non-familiar liquid, and so on. So this just give two examples. This is to study the superconducting material. This at the Swiss in the PSI. So they can study the magnetism, and also is study this is in the US list to study the spin excitation in the quantum magnet. And now it's very popular to use the neutron scattering in a continuous matter to study high TC superconductors. So they can detect the probing the bond structure and the Fermi surface in high TC. And this is the results in the PRL. And also can study the spin waves. So this also is an important direction, interesting direction in the superconducting studies. And the neutron has large cross-section to light element. So this is the cross-section of the nuclei to the synchrotron radiation or to X-ray. This is the neutron cross-section to the nuclei. So you can see for the helium and for the lithium, for the carbon, for the oxygen, they have very big cross-sections. And those elements actually is very important for many studies. This is just to show if you just use the synchrotron radiation to measure this protein molecules. So you only get this information. But when you combine it with the synchrotron, with the neutron scattering, then you can get much more rich and more comprehensive information about the molecular structure. This also is the for high TC superconducting study and many structures. And for the energy, so the neutron could study the solid oxidized fuel cells. So this study provided interesting results about the new type of the cells. And this is for the hydrogen storage, metal organic framework for the hydrogen storage. That also is a very hot issue at the meantime. So they can get very important information since the neutron very sensitive to the hydrogen and to the organic elements. This is the lithium battery. study. Since the neutron has no charge and high penetration, so you can do it. You can put the battery into the beam line and doing the in situ study of the structure evolution in the batteries. So this actually is done by Professor Xunli Wang he was in the Oak Ridge, now is in the City University of Hong Kong. So that's give many important information and more understanding about the batteries. And another important issue in energy is the flammable ice. So people say there is a bigger reserve of such kind of ice under the South Sea. So, but those kind of ice must be only exist in the high pressure, low temperature. So with the you need a container to provide the pressure and the low temperature. Then you can study the structure. So the neutron scattering provide an idea to study those kind of flammable ice. So this is the typical results from the study. So they can penetrate the container, high pressure container. Also, they are sensitive to the hydrogen and the carbon. So they can provide you very detailed information. And neutron scattering widely used in the soft matter. So they can study from the 1 angstrom until 1 centimeter in a wider range for the material, for the life science, for the DNA, and many interesting part could be studied by neutron scattering. So this is the biomaterial with the neutron instrument. So this is the different typical study with the biological researches use the neutron scattering. And this is to study the DNA. So with the neutron scattering, we can get much more rich information about the DNA structures. So the advantage is the neutron is more sensitive to the carbon, to the oxygen, and the helium. Another interesting applications is they can study the large component. We can use, for instance, the Rutherford Spallation neutron source called IAS. They have a very good application for the German high-speed train. They had an accident, bad accident, more than 10 years ago. So finally, the study of the railway wear of the high-speed train was carried out in the IAS. So from the detailed study, they can identify the problem and find a way to avoid such kind of accident. Also, they can do use the diffraction measurement for the welding stress for the aircraft, tubing, planes, and the discs. So that's and also could study the glowing of soil, the root glowing of the soil. They can also study with it. Another interesting applications is the new type of the welding called the friction stir welding. So that's a new type of the technology. For the new type of technology, when you weld in two types of materials, you do need to study the the manufacture procedure, optimize the procedure to understand the temperature distribution and the stress distribution during the welding. So now they can put the machine, the welding machine, into the beam line, and you can make a measurement of the temperature and the stress distribution during the welding. So then you can choose the best manufacture parameters. Another example is in the Rutherford lab assays. So the Airbus 380 wing, the many manufacture parameters were optimized in this neutron source for the welding and the many procedures. So they can carefully study the stress distribution and find the best parameters for the manufacture. Another interesting is the shear thin, means the liquid. Typical liquid is tomato ketchup. So how they can optimize the tomato ketchup, the liquidation. So they can use the spallation neutron source to study, and there is the typical results. And actually this is for many industry applications are very important if you want to understand the thick, complex liquid. So I do not go to much details. I just give you some hints about the neutron scattering applications. So finally, I just give a few plots to show how was the neutron scattering, why the neutron scattering had wider applications. Because the energy of the thermal neutron is very close to the excitation of the energy of many dynamics behavior in the matter. So this is the wavelength, this is the energy. So you can find many research field. Almost all of field in the material science and contents matter, life science and so on. They can find the corresponding wavelength and energy. And this plot showing from the 1 picometer to millimeter. So you can use different neutron scattering technology to study the material structures. So for the large piece, you can use neutron imaging until, so use the power neutron deflection to study very small scatter. And also, the neutron scattering could study the dynamics, not only structure, because the neutron has wide momentum match with the many reactions. So this also gives from the different time scalar and different energy. They have different neutron scattering method to study the process. So I believe the neutron scattering provide strong tools for many applications. The neutron scattering could be carried out in the two types of facilities. One is the nuclear research reactors. Another is the spallation neutron source. So this table compared with the reactor neutron source and the spallation neutron source. So the advantage of spallation neutron source is high pulsed neutron flux. So they have a very good timing structure, could provide much more information, and they have rich shortwave neutrons, and they have a lower thermal power, lower background, free from nuclear fuel. So this is very important at nowadays, particularly at Europe, because they have a strong group against the nuclear reactors. So, but the spallation neutron source, the construction and the operation is much more challenging compared with the synchrotron radiation source. Now, I think in the world, there are more than 70 synchrotron radiation sources in the world. Even a country like Thailand, even Jordan or Singapore, they have a light source. But for the synchrotron, for the spallation neutron source, is much more complex in technology and much more challenging. So now there is only 3 spallation neutron sources in the world operation. So the operation is IAS. So they started running 30 years ago. Now still produce many interesting results. And in the Oak Ridge lab, they have a US spallation neutron source. So their design power is 2 megawatts. And the Japan, JPAC at Jerry, Donghai, so is 2 megawatts. Our China spallation neutron source is 100 kilowatts and could upgrade to the 500 kilowatts. And we will open to users by 2016. Recently, in Sweden, Lund, European spallation neutron source started construction. So they probably will start in open to users by 2020. So hosted by Sweden and Denmark, and other European countries also joined, like Germany, France, Italy, UK, and other countries. Because except in France, in many European countries, the reactors, research reactors will also be closed. So finally, they have to use the spallation neutron source to do the neutron scattering study. So now I would like to give some introduction about the China spallation neutron source. The China spallation neutron source, the site is in Dongguan, not too far from here. So this morning I came from Dongguan. It's a 1 hour train from the Changping, which is a railway station. And after 70 minutes, I arrived at Hongkan. I don't know how to pronounce it, near the Hongkan. So it's very, very easy to reach here. Actually, you can go in the morning and back in the evening. So they have a NILAC accelerator from the ion source, RFQ, and the DTI accelerator, provide 80 MeV protons. Then go to the rapid cycling synchrotron, is the storage ring, increase the energy to 1.6 GeV, and hit the target. In the phase 1 is 100 kilowatts. And we already keep the room for the facility to upgrade to the 500 kilowatts. So we already have additional tunnels for the superconducting cavities to increase the beam energy from 80 MeV to 250 MeV. Then the storage ring could provide 500 kilowatts. So we have 25 hertz cycling, 25 hertz. The US spallation neutron source is the 60 hertz. So finally we can reach the 500 kilowatts. So essentially, every neutron pulse, we will have a similar neutron flux to the US spallation neutron source. But our design is much more simple, much cheaper, and more reliable. So recently, we had several discussions with the Oak Ridge people. For the target to work at 1 or 2 megawatts, they need a Mercury target, which is very complicated. So during the last 4 or 5 years, the Oak Ridge changed the target 13 times. So it's a big mess for them. And also the Mercury target is bigger. So once your target is bigger, for the high power, so finally the neutron flux is not proportional to the power. So the Oak Ridge is going to build the second target. So they will use somehow similar to our design, not use the Mercury target. So that's a new common understanding. Institute of High Energy Physics is in charge for the project in a collaboration with the Institute of Physics, Chinese Academy of Sciences. So they have more teams, long history work for the neutron scattering. Design philosophy. We build in facility within the approved budget and the time schedule. So our phase 1 budget is about $250 million. And the US and the Japan spallation neutron source is 1.4 billion and 1.8 billion. So it's much bigger investor. And we have to finish in the 6.5 years construction period. And we build advanced facility with the upgraded potential. So 100 kilowatts beam at phase 1 with minimum costs, low energy NINAC, and high energy rapid cycling synchrotron. And this facility could expand to 500 kilowatts at phase 2, use the superconducting cavities to increase the NINAC energy 250 eV. So essentially, the superconducting cavities for high power proton, we already succeed in our institute and pass the test. So once we finish the construction, we can start the upgrade to increase the power right away. And we have to adopt the proven technology to reduce the risk, because this is the first high power proton beam facility in China. And also as a user facility, we have to keep high operational reliability. And we have to develop the domestic technology to control cost, keep final fabrication in China as much as possible, and close collaborate with the world leading spallation neutron source. So this is the neutron source in the world, and this is the so now basically the new facility basically are the spallation neutron source based on the high power proton accelerator for this end, and this is the US and the European spallation neutron source, and this is our spallation neutron source. So actually we can provide a similar neutron flux per pulse. And people asked why we choose the Dongguan. So I think that's a bigger question to us. So the Chinese Academy of Sciences would like to optimize the distribution of the large research infrastructure, not concentrate only in the Shanghai and Beijing. So they realized the economy in the Canton are very strong. So the GDP of Canton will soon already close to the Korea. But the scientific research of the Canton and high tech in Canton is much worse than the Korea, worse than Taiwan. So the Chinese Academy of Sciences would like to work together with the Canton to promote the science and the technology in this area. And the Canton, they have a bigger pressure to keep the sustained development of the economy and to upgrade their economy. So they welcome us to construct this facility in the Dongguan and provide strong support. So they give us 500, $500 million money, $500 million renminbi match fund, and give a large free land and road, dedicated road, transformer station. The most important is they agreed to in charge in the management of civil engineering and will take care of the deficit of the budget of the civil engineering, if any. Because we are physicists, we are not good to deal with the construction company. And there is big uncertainty. So to support us, so they agreed to manage the construction and to pay any deficit. So now the civil construction is 550 million Chinese yuan. But the deficit now looks like it's about 200, additional 200, because they found the foundation is not as good as expected, and many other factors. So that's the very strong support from the local government. So here is Hong Kong. So here is Hong Kong, and this is the Dongguan. So actually, we just in the highway from the Humen to Changping. Changping is the railway from the Hong Kong to Guangzhou. So they start in the Changping. So it's 50 minutes by car from the Shenzhen airport, or 1 hour train from the Hongkong, plus 25 minutes car from the railway station to our facility. So it's a very convenient location. And this lists key milestones. So the idea actually is discussed 15 years ago. And finally, we started the construction at September 2011. And so we expected to have first beam on the target by September 2017. And 3 years from now, we completed the project and open to users. In total, is 6.5 years. China's Spallation neutron source belongs to IHAB. IHAB established a Dongguan branch in the Dongguan. So Chinese Academy of Sciences opened 400 positions for the Spallation neutron source. So now we already hired about 250 persons for this branch. And we also have about 140 senior physicists and engineers from Beijing to work at the Dongguan. So they became the backbone of the project, also training the young people. And I have provided the strong support to the construction, commissioning, and the research of the China Spallation neutron source. So the Dongguan will not be independent institute. So the idea is the following. In many cases, like in nanoscience, Chinese Academy of Sciences build some new institute in Suzhou, in Ningbo, and so on. So and those institutes finally will fight each other for budget, for project, for the scientists, for good scientists. So, and we believe as a branch is much better to meet these challenges because the high power proton accelerator required very complicated technology, very complicated team. So unless the Beijing, I have the Beijing to treat this Spallation neutron source as their own business, not a potential competitor, then this is you can build. And also you build a team here. This team could also to work in the future. Any project in the accelerated facility project in China, like Beijing Net Source, or like the China, like the large E plus mass collider. So I think that's the way we think about. Like in the UK, so they just put Dustbury and Rutherford together, not two computation institutions, but they put it together. So that's much better to manage to meet those challenges. That's our basic idea. So I would like to give the progress of the construction. This is the plot of the facility. So the major facility is proton, rapid cycling synchrotron, target, and experimental hall. So this is the utility for the facility, and this is the office, lab, and guest house and canteen. So this yellow part was built by Canton province money. All of them have finished. This red part is built by central government budget. So this is the site was the very good, actually is a lychee. All of these are lychee. Is one of the best place in the China for the lychee. So we take this place, and this is before we start the civil construction, and this is the photograph 2 months ago, before the Chinese New Year. So this is the Proton LILAC service building. The accelerator is underground. This is the storage room service building. The accelerator is underground. This is the target and experimental hall. And about 85% of civil construction finished. And it should be finished all of civil construction by autumn this year. And this is the LILAC tunnel. We already started installation. This is the outside. Means basically for the microwave, klystron, power supply, control, and so on. This is the storage room, underground. And this is the storage room building in the surface. So they will have a power supply and a control system for the accelerator. And this is the target building and the construction. This is two are the transportation beam lines. So in October 15 last year, we started the construction. We started installation of the accelerator components. And this is the assembling and the testing hall. So for different machine components. And this is the target construction. This is very challenging because once the target started operation, so it will be irradiated. It's hard to repair, so you cannot make a mistake. So this is the real target is inside, and the surrounding ion blocks are shielded. Then they shielded by heavy concrete. This bigger box we call the hard shell. Means for the target components, we have to maintain. So when we maintain, we use the robot to take out the target components and shift into this hard cell using the remote operation to maintain it. So this is the bigger box, then put the heavy concrete outside. This is the birch field at the beginning of the December. So you can see this is the lab, office, and the guest house. This is the utility building. This is the real facility. This place now is the temporary barrack for the construction company. So this place will be reserved for the second target system in the future. So this actually, after this mountain, this is Shenzhen, called Guangming. I think it's a big town in the Shenzhen, is Guangming. So just in the south of the Dongguan, very close to the Shenzhen. And this highway is Humen 到长平, this is the highway. The utility installation going well. You can see those for cooling water, pumps, electricities, and also for the accelerators, they have cooling pipe, cables, transformers, and all of those are going smoothly. Progress of accelerator system. So the NILAC is the H- ion source, RFQ. This is the radio frequency quadrupole. This technology was invented for Star Wars of the Mr. Reagan because they want to some compact accelerator can produce the ion beam, can produce the beam in the airplane, big airplane like a Boeing 747 to shoot the satellite or missiles. So finally, it doesn't work, but it gives a good technology for the particle physicist and for the spallation neutron source. Then they go to the DTL, LINAC. So that's the major parameters. And this is the design of the ring. The circumference of the ring is about 230 meters. 230 meters. And so the accelerated construction going well. This is about the accelerating physics. This is the H- ion source already installed in the tunnel. This is the RFQ accelerator also installed in the tunnels. And this is the NILAC accelerator called the DT drift tube NILAC. So this is produced by machine shop of IHAB. This is the RF system, magnets, power supply, ring, RF. And the vacuum, this because we have 25 hertz cycling, so the beam pipe must be ceramic, cannot use the metal as the normal accelerator. So that's a very complicated technology. So for the part of the ceramic beam pipe, we bought from Germany, part produced in China. So this is the magnet in the test hall and for the field mapping, and this is the installation of the drift tubers, and this is the test of the power supply. About the target station and the instruments. So the design consideration is we would like to get a high neutron production. We use the constant target, billion refractor, heavy water cooling. And after the neutron produced in the target, they have to go through a modulate. we have three types of modulator. We have a decoupled modulator, is the water. And the decoupled poisoned modulator is 20K hydrogen. And also is 20K hydrogen is coupled. The three type of the modulator means they slow down the velocity of the neutrons, to convert them into the wavelengths need for the neutron scattering experiment. And we have and we work at 100 kilowatts, but we could, with a smaller modification, upgrade to 500 kilowatts. This is the sketch of the experimental hall. The proton beam from here, and this is the target. And in the two sides, we have the experimental hall. In total, we have 20 beam lines. And here is the so-called hot cell, which I show you. So to maintain the component of the target. This is the parameters of the two phases of the target. And this is a sketch of the target station. It's another complicated. And this is the neutron instrument distribution from the three types of the modulator and the 20 beam lines. Because of the limited budget, we only have 3 beam lines at phase 1. So I will give a short report about these 3 beam lines. So in total, we could have 20 beam lines. I think that's the normal. In the US SNS, in the phase 1, also is 3 beam lines. Then afterwards, they construct more beam line from the DOE money, from the user community, or from the industry. The Japanese spallation research, they also is 3 beam line. Afterwards, the local government provide and the companies provide more money to build more beam lines. So first is the general purpose powder diffractometer. So for many users to determine the crystallographic and magnetic structure in general purpose. So in my previous slides, I have to show for the which scalar of dimension and time you could use this powder diffractometer. So for the different purpose, you have to use different spectrometer. The resolution is 0.2%, which is very good performance. Second is general purpose reflector meter. So basically, is study the solid film for the chemistry, for the magnetism, for the life science, and so on. So they study the reflectivity and the deflections. The resolution of the Q value is 1%, and also can carry out polarized analysis, and so on. The third spectrometer is small angle neutron scattering. So they can study the scalar between the 0.01 to 0.5 Armstrong. This is the wavelength. And the resolution is better than 30%. So they can, I think this has the most wide applications for many research fields. So this is the target system. The design is finished and then the manufacture is underway. And we will start in the installation by end of this year. And modulate is very complicated structure. So the Chinese Academy of Engineering Physics, 9院, they made this for us, very precise, very challenging. And the neutron chopper, so that's also is a very complicated mechanism. So now we already had a prototype and going well. We made a great effort to promote the neutron instrument. So the physics design of 3 day 1 instruments fixed, and the frame of the control and the data management analysis defined. And so the construction started in the October. We started in October this year for installation. We also made a great effort to promote user community. So there is a China Neutron Scattering Society, which is a branch of the China Physics Society. They coordinate the neutron scattering development roadmap, the people training, and the collaborations. So the facility at the meantime is the CAR, the China Advanced Research Reactor in the China Institute of Atomic Energy, and the Mianyang Research Reactors in the Chinese Academy of the Engineering Physics and the China Spallation Neutron Source. So every year we have user meetings. Last November, we have the meeting in the Mianyang. So we have more than 200 delegates and from the 59 institutes and the universities. And we also use the band scattering neutrons.
Where do you stand, maybe?
Yeah. So you see, this is the neutron from the reactor. So they make a turn before hitting the target because they don't want to band scattering neutron go back to accelerate. But the band scattering neutron actually is a very good neutron source because they have wide wavelengths. We call the wide neutron source. So we get a free neutron source. This is the first wide neutron source in the world using the Spallation neutron source. So they can make a lot of measurement for the nuclear reactions, for the astrophysics, many reactions. So it's very interesting. We have strong international collaboration. We have an international advice committee for accelerate and for the experiment. So every year we have the meeting, and this was the meeting last December. We made the proposals to the Material Genome Project in China. So we are going to apply for the 5 new spectrometers in the Spallation neutron source: full neutron scattering spectrometer, engineering material deflectometer. This basically is doing like the big mechanical piece studies. And magnetic neutron scattering spectrometer, electromaterial spectrometer, and the neutron imaging. Also, some university like Zhongshan University, Jilan University, they are also interested to build spectrometers according to their interest. Finally, I would like to say a few words about to promote the neutron scattering in Hong Kong. The China Spallation neutron source provides the Hong Kong scientists and engineers a unique opportunity for many research fields like material science and engineering, contents matter, chemistry, life science, environment, energy, and resource. So today I just give some examples. I believe for the advanced researches, you have to use the latest facility to do your research. Like Chinese saying, 君以善其事，必先利其器. In English, they translate the king wants to do good, must first sharpen his tool. I think it is important for Hong Kong scientists and engineers to carry out many researches with the spallation neutron source. I believe this became a very powerful tool to obtain good results. And since the China spallation neutron source so close to Hong Kong, the Chinese saying is 近水楼台先得月. Water from the towers, the first to catch the moon. So I suggest the Hong Kong scientists, engineers think about how go ahead with the neutron scattering. So the neutron scattering is taking a route in Hong Kong. Now mostly is at the Hong Kong City University of Hong Kong, the Professor Wang Chunli. I mentioned his results for the lithium batteries. Means he is one of leading physicists in the neutron scattering for material science. He now is the chairman of the City University Physics Department. And also, Chinese Academy Science and Culture joined the lab, made a special joint lab for the neutron scattering in material science. So we have a lot of activities, like we organize some schools every another year. Also, you know, there is a very good conference series called the Golden Research Conference. So they have a meeting, they have a conference June this year, and also is every another year. So I think the neutron scattering in Hong Kong already started. What my suggestion is more universities should hire faculties for the neutron scattering for build up a critical mass using the China spallation neutron source and make it a premier center in the neutron scattering. I think this is a good opportunity for Hong Kong. Another is also the Hong Kong scientists and engineers could think about what kind of neutron scattering spectrometer is most useful for your research field. Then you can think about to build a neutron scattering spectrometer in our spallation neutron source. I think that's another thing we should think about. Last but not least is the training young people, because we do need young generation. They understand the neutron scattering and its application in their own research field. So we should send those students to summer schools, to the conference. More important is to working in the foreign spallation neutron source. So if you're doing certain type of material science, you can find in the Oak Ridge, in the Japan, or in the Rutherford, they have a similar experiment. You send the young people go there, and we can recommend your people go there. And especially nowadays, program in the UK called Imagine Power, especially to support the scientific exchange with China. The 英国的这个科教大臣 Minister of Science and Education visited us a year ago, visited Spallation Neutron a year ago, and Oak Ridge, the Rutherford is very much support, and they produced a lot of good results in the material science, life science, medicine, and so on. So I think that's a good opportunity for many research fields to open a new page in Hong Kong. So finally is the closing remark. Spallation neutron source. The civil construction finished about 85%. Utility installation going well. Many systems are available now. The manufacture of accelerated and experimental systems are going smoothly. The installation started. We expect the first neutron beam by September 2017 and open to users by spring 2018. We made a great effort to promote the user community and to prepare the day one experiment. China's Spallation neutron source provides Hong Kong scientists and engineers a unique opportunity for many fields. Neutron scattering applications should be promoted in Hong Kong. We look forward for more collaborations in the neutron scattering applications and instrumentations. Thank you.
I don't know. Any questions?
Very interesting talk, and I'm glad to hear that you're trying to promote the interactions with the people in Hong Kong. So if things will come online, hopefully in 2018, but what about set up for experiments, and when would the announcement be for maybe submitting proposal for experiments? Would that be the year before?
I think probably within 1 or 2 years, we will open to user proposals. And we believe the day one experiment is very important because you have to convince your value to the funding agency, to people. So we will run the facility according to international conventions. It's free of charge to users. And every beamline has a committee, user committee to select the proposals, not decided by us, but by user committees to select the experimental proposals, as you mentioned. I think probably in 1 to 2 years we will start.
And do you anticipate that end users will also go to participate in the experiment with your staff scientists there? Or
of course, because
situation.
Yeah, I think particularly at the beginning is we do lead our home scientists and the instrumentation people work together with users to make sure the experiment doing properly.
Just because you mentioned about the CTU already has some access to this kind of neutron scattering experiments, so I'm just curious at this stage if Hong Kong scientists or engineers would like to do the experiment using neutron scattering, or where could they get access to that? And one more question is, I heard that in US sometimes you might only have several samples per year using this kind of neutron scattering. So I'm just wondering, after 2018, once that we can get access to the CSNS, how often and how many samples actually per year could be actually applied to?
Certainly, to promote the team is a big issue. So first is, as I mentioned, there's 2 reactors. They can provide the neutron scattering. So it's not not as good as spallation neutron source, but it's a good beginning. And also we attract many young talents back to the spallation neutron source. So, and we also send many people from us and from the universities go to the foreign spallation neutron source to get experience. Only the people has good experience at the existing spallation neutron source, then they could get reliable results for our day one experiment. And for the second question, you mentioned is the beam time is very tight. That's what you are saying? You mean in the US, you only can have a few samples? Yeah, certainly the problem of the spallation neutron source is the experiment take a much longer time compared with the light source. In the light source, you change your sample with the robot. Maybe every seconds or every minutes you can change it. In the neutron scattering, it takes a longer time. Certainly, I think there is a strong, once we can produce good day one experiment, certainly the demand to the beam time will be increased soon. But I believe we are going to increase the beam line for users. If for certain type of the experiment, the demand is very high, we can build additional beam line for them, even for the second target station.
I have a question on the design and the construction. How much of the design was done by mainland Chinese scientists, and how much did you involve the international community?
All of the design is carried out by us, with the reviewed by international experts, but designed by ourselves.
For the construction, you mentioned some of the technology, for example, you imported from Germany and so on. Can you give a rough figure how much of the technology is homegrown in China?
That's too hard to give this number because certainly we try to learn the experience from the other spallation neutron source. And I think for the scientists, the most of the cases, they even can give their drawings, give us their drawings. We can improve their design, adapt to our needs. I believe probably more than 1/3, they have a strong background from the helpers of the foreign spallation neutron source, 1/3. But finally, every detail, every design, we have to carry out by ourselves. And also, we meet many problems in the prototype. And those kind of things we have to, we certainly will discuss with the foreign experts, but finally, probably we will find the solution by ourselves.
Just as an end user, if you just do it sort of a long-term operation down the road, so the neutron fan will be free, and the end user, they just use their own travel budget and fly into the place, and they give us how many days, 5 days, 3 days, beamline time, then they just get the experiment done, take the data and go back. Is it the way you sort of like in the US, you plan to do? Or
Yes.
China,
Yes.
you can get the money to build it. It's very hard to have a high standard maintenance.
I think that's not completely true. Like we have Beijing single-rotation rate, we have Beijing Electron-Positron collider, which work both for particle phase collision and for light source. We receive the 100 million yuan per year for operation. For Shanghai light source, they have similar budget. So I think we will follow international convention. Free use for all of domestic and international users. And for the user will collect the data and bring back to home. In addition, we will provide the many analysis method, because it's not all of users are expert for those analysis at the beginning. So certainly we will provide many packages for different type of analysis. I think that's the way. Means I'm the project manager. I understand the success of the project of such kind of facility is not mean you build and you reach certain energy, certain power. The judgment is how good the results from your facility were produced. That's why when Henry invited me, I came here just in 2 weeks, because I think it's important to invite the Hong Kong scientists, particularly Hong Kong University of the Science and Technology, which has very good potential, to think about how to use this facility to carry out your own research, produce first-class results.
Okay, so let's thank Professor Chen. Since you've been Dongguan a lot, it's easy to contact you.
And you are welcomed to visit Dongguan. I think it's not too far from here and very easy to. I think you can. You organize a tour. So I think it's very impressive. And for those kind of things, we're doing very fast. Thank you.